So we're moving into section 5.2 now, which is about exponential decay functions. And we've been talking about exponential growth functions. So this is sort of the natural second half of this material. And you can probably sort of imagine what an exponential decay function looks like. It's one that gets smaller over time. So if I draw an exponential growth function, they pretty much look like that. Exponential decay looks like that. Okay. I suppose actually when I said you could imagine it, I guess you could actually think of other things that decrease that you might have put in here. So for example, you might wonder, well, what about this? Wouldn't that be exponential decay? Well, it's certainly a decreasing function, and it could be an exponentially decreasing function. But we are not going to look at this type of function. When we say exponential decay, this is what we understand to mean. Okay, so I'll just go ahead and get rid of that. Okay, all right. So let's look at a set of data. This data is modeling the amount of a drug in milligrams present in the bloodstream after it's been ingested. And so we've got 0, 1, 2, 3, 4, 5 data points, and then the associated milligrams for each. And you can see that they're going down over time, right? So if we graph this function or put it in the calculator and look at successive ratios, you will in fact see an exponentially decreasing function. And so just to remind you, how do we verify that it is exponentially decreasing as we look at this successive ratio stuff, which is a little bit harder to put in the calculator, but you can certainly do it. So as I was saying, we do have exponentially distributed data, and we can check this to be sure by looking at your successive ratios. There's not really a real slick way of doing this in the calculator, except I think the quickest way is just to divide it by hand. But in any case, we do have exponentially distributed data. And notice that for the average rates of change, so they're all negative, but they are negative in the sense that they are also increasing. So when you look at these numbers, if these were positive numbers, we wouldn't say they were increasing, but since they're negative numbers, we say they're increasing because they are going closer up. They're moving upwards towards 0. So that's actually increasing. In terms of rate, we say this is decreasing at a decreasing rate, which is concave up, and decreasing at a decreasing rate. Okay. So the point of all that is to show you that what a exponentially distributed data set looks like that is decreasing. Okay. So let's make this more formal and actually talk about what a decreasing exponential function looks like in terms of its function. And so we've got f of x equals a times b to the x, and that looks exactly the same, as our other general exponential growth form. The only thing that makes it different is what we actually let the value b take on. So we're only going to let b be numbers between 0 and 1. So, b could be 0.93 or 1/2 or 0.05, etc. Okay, but b cannot be larger than 1 or equal to 1. If it's larger than 1, then we don't have decay, we have growth. So that's the thing that makes it different, is that line between numbers smaller than 1 and numbers greater than 1. And when we have a base that's less than 1, we call this the decay factor because it's going to actually be decaying rather than growing, and so it's a factor, but in particular it's a decay factor. Okay, and just like we defined the growth factor when x increases by 1 unit, f of x decreases by a factor of b. So it's a multiplicative decrease, okay? So just to be perfectly clear, b is, whoops, almost wrote the wrong thing. B is decay factor. When b is less than 1, and when b is greater than 1, b is the growth factor. So notice that I'm only talking about the factor here, and as you know from section 5.1, the very next thing that we talked about after the factor was the rate. We talked about the growth rate, and so yes, we are going to talk about a decay rate now, and this tends to be one of the areas where students get confused, and you'll see why. It's mainly notational, but let's take a look. So here's our exponential decay function written in rate form. Okay, so we can write this as f of x equals a times 1 minus r sub d to the x. So what in the world is r sub d? Well, the subscript d is meant to indicate decay, and r sub d is the decay rate. So it is the decay rate expressed as a decimal value, not as a percent, just like we did for the growth rate. But there's two things I want to really pay attention to here. One is that this is a minus sign here. Oops, my arrow got kind of off where I wanted it to be. So notice that minus sign, but notice also that this RD is a positive number. Okay. So the way that we express this is 1 minus a positive number. Okay, and that's in terms of decay rate. Okay. And what's the connection between the decay factor and the decay rate? Well, the same as it was for the growth factor and growth rate almost. It's b equals 1 minus rd. So for the growth rate, that was b equals 1 plus r, right? For growth. Okay. So it kind of looks like in some way that the only difference between growth and decay is that you have a minus sign that we insert in there, and that's pretty much true. So in fact, decay is equivalent to negative growth. This tends to lead to some confusion, but you could actually define all of this stuff in terms of decay rates. You could just never talk about decay rates and just only talk about negative growth rates. That would be okay, and it would work. So specifically, what do I mean by that? Well, we have this growth function form, f of x equals a times 1 plus r to the x, and r is the growth rate. But if we have a positive growth rate, then we just have normal growth as we are used to. But if we have a negative growth rate, then suddenly we don't have a growth factor anymore, we have a decay factor. Okay. And this is really just terminology, because if I have negative growth, then with the negative growth rate, then really in essence what I have is positive decay. So a growth rate is equivalent to a decay rate with the same magnitude but the opposite sign. And as we just stated in the other slide, the base and the growth rate are related by this equation, b equals 1 plus r, where b is just the general factor and r is the growth rate. But the thing that's kind of hiding in this equation is that I'm not specifying that r is positive here. So that can lead to some confusion. So I'll just show you some examples of this. So for example, if I say I have let's say the growth rate is -5%, then the decay rate is 5%. R is -0.05, and R sub D is +0.05. And the factor is 1. And there's two ways I could write this. I could write this as 1 minus R sub D, which would be 1 minus 0.05, which is 0.95, or 0.95. That's my factor. Or if I want to write it in growth form, I would say 1 plus R is equal to 1 plus a -0.05, and that's the same thing as 1 minus, right? And so that's 0.95, and again, that's my factor. So you see how this might be a bit confusing. I hope it's not, but we just have to keep our terminology straight. So one way to kind of drive this point home is that let me clear all that. Is this? I could say that we have a negative decay rate, and that would be positive growth. But that's very confusing. So just to kind of perhaps clear the water a little bit, I hope. We generally don't ever say we have a -5% decay rate. Okay, so that would pretty much never be said. I mean, it's not like necessarily incorrect to say it that way, but it's very confusing. So if we're talking about the decay rate, it will probably be phrased in positive terms, but you have to remember that since it uses the word decay, that we actually turn that into a negative when we compute with it. Okay. All right, so I hope that's not too confusing. I'm going to go back to the slides now and get some more experience with this, and hopefully it'll become more clear. So here's an example just to kind of straighten things out. We've got a function, an exponential function. We have the initial value of 100, and then you have the factor of 0.9. And notice I'm just calling it a factor. I'm not specifying growth or decay. I could, though, because it actually is a decay factor, but I'm just calling it a factor. So 0.9. So what's the growth rate? Well, the growth rate is -10%. And here's how I got that. Or, that's in decimal form. But how I arrived at that computation was I say, well, R equals B minus 1. Where did that come from? Well, that comes from B equals 1 plus R. So if B equals 1 plus R, then R equals B minus 1. That's just doing a little bit of algebra. And so B is 0.9, and 0.9 minus 1 is negative, hence -10%. All right, if we want to talk about this in terms of decay, the decay rate is just the negative of the growth rate, but since the growth rate itself is negative, then that's a double negative and therefore positive. So the decay rate is a positive 10%. Now, a positive decay means that it is actually decaying, and therefore we decay by 10% each hour. All right, so we're gonna do more examples here in the next video.